Hello, calculus students. This problem is from 2008, number 3. And for my AB students, this is from page 75. This problem covers quite a bit of stuff. It will cover related rates. It will cover maximums, and we might even see some fundamental theorem of calculus. So this is a calculator okay problem. So remember, even when you have a calculator okay, you must show the calculus setup. You don't need to integrate by hand or take derivatives by hand, but you must show that calculus setup. So let's go ahead and look at this problem. We have oil leaking from a pipeline, and there's some cues here that tells me that we might have a related rate situation. And I'm going to emphasize that. When I see something like the volume is increasing at a constant rate, okay, so I see that and I think, well, this has a little bit of that related rates flavor. The second thing I notice is that we do have this right circular cylinder, and it talks about both the radius and the height are changing with time. So anytime I see something in a calculus problem that says changing with time, it lends itself to related rates. The good news is the College Board tends to be kind and give you those geometric formulas that you might need. And so in this case, we net that volume of that right cylinder. Pause the video and take a moment to read part A. That's where we're going to begin. Okay, so when I see things like at the instant, this is a related rates problem. As soon as I see that, it says at the instant when the radius of the oil slick is 100 centimeters. So what we know is we have the radius of 100 centimeters of this oil slick, and the height is 0.5 centimeters. The radius is increasing at a rate at 2.5 centimeters per minute. So these are things I want to write down immediately. So I have dr dt, the change in radius with respect to time, and that equals 2.5 centimeters per minute. Okay, what is the rate of the height with respect to time? So what we're looking for is dh/dt. So if you remember when we were in the related rates unit, I said you should always think about, you just took a picture of the situation. You took the picture of the radius when it was 100 centimeters and the height was 0.5 centimeters. And then you took another picture a moment later. And what you need to ask yourself, will the radius change? And will the height change in the next moment? Because we need to decide if they will remain constant or if they will change as time changes. We need to make that decision prior. So pause the video and think about that. So this one is really tricky because if we had a mold of a cylinder, for example, we have a cylinder container that's being filled, anytime we would take a slice out of it, that radius would not change, and that would be a constant. The difference in this problem is the oil slick takes on, if you look above in the original problem, takes on the form of a right cylinder, circular cylinder. And so imagine that oil filling, it's going to, that circular base doesn't stay constant, it spreads out. So the radius does change in this situation. It doesn't have that rigid form. And so you've got to think about that. So what we're going to do now is we're going to do some implicit differentiation. So we need to take this volume formula to take the derivative of all variables with respect to time. So I want you to decide what derivative rules you might need to apply here. So we need to do implicit differentiation, and we cannot forget we have a product rule since neither r or h is a constant. So we have dv dt equals pi r squared times dh dt plus h times 2 pi h times 2 pi r dr dt. So pause the video, put in all the information you have, and find dH dt. So here's my answer. dH dt equals 0.038 centimeters per minute. This is a problem that's worth a lot of points. So this is worth 4 points. So I'd like to kind of break that down with you. Some of these are just give me points. And so this is why it's important to write down what you know. You get 1 point for just identifying that you knew what dV dt was. Now, if I look at my problem here, I did not write down in my work dV dt equals 2,000 cubic centimeters per minute. However, I did apply it here. So as long as I applied it, I would be fine. But if I couldn't apply it, I wouldn't get the point. So I would need this and dr dt. Those two things underlined in orange gives me 1 point. Okay. This right here gives me 2 points. And then my final answer gives me that 4th point. Pause the video and read part B. So I'm hoping you've read through this and you realize, so our oil is still leaking at 2,000 cubic centimeters per minute, but now we have a new rate we've been introduced to. We have the rate in which we're recovering, we're cleaning up the oil. And we've also been asked to maximize the volume. So I want you to just take a moment and ignore the problem and think about, in calculus, what do we use to maximize? And the answer is we use a rate of something. If I want to maximize volume, I need the rate of volume with respect to time. But I need a specific rate. I need the rate of total amount of oil. So if I want to think about that total amount of oil, and I want to create that total volume of oil, I'm going to think about it this way. I need the rate in which the oil is leaking minus how much rate, or I'm sorry, the rate in which the oil is being cleaned up. This goes back to that in-out problem where, where we have things coming in and we have things going out. So this is the rate of change of the volume of the oil with respect to time, the total amount of oil. Again, oil leaking minus oil cleaning up. So what we have to remember is we want to find when that equals 0. Okay? And so we're going to take this 2,000 minus r of t and set it equal to 0. And so this is pretty straightforward. We need to figure out, so r of t equals 2,000. That gets us 1 point. So even if you're not like sure where to go from here, make sure you write that down. We've got that. So I need to figure out when that happens. So I need to go to that r of t equation. And so we were given that r of t equation. I'm just rewriting it so we have it in front of us. And so what we're essentially doing is figuring out when this equals 2,000. Though you should be able to do this without a calculator. This is a calculator okay. So take a moment, pause the video, and see if you can figure it out. So me being the math person I am, I want to do this by hand. So I get the square root of t equals 5. So t equals 25 minutes. Just because r of t, we can figure that out, that 25 minutes, that's this, that dV dt equals 0 there, doesn't mean we have a maximum. So we might want to think about it this way. We might want to think about a sign chart, correct? So again, I'm going to encourage you to either look at that graph on your calculator or come up with a sign chart to support your answer. So you could see my sign chart and you could see my write-up. You want to make that statement. We needed the justification. So my answer, 25 minutes, I have another point, right? So I got a point here for R of t equaling 2,000, I said, and then t equals 25 minutes, and then my justification. So at this point in time between A and B, we're at 7 points. I'd like for you to take a moment, go back, and read part C. By the time the recovery device begins removing oil, we have this 60,000 cubic centimeters of oil has already leaked. So there's my initial value. I need to write an integral, but do not solve. That gives the volume of oil in the time that was found in B. Okay, this is a typical fundamental theorem of calculus. So we're trying to find the max amount of oil is what we're trying to do. And so in order to find out the total amount of oil, we would need to integrate from 0 to 25 the expression we created back in part B. Right here, I'm putting a box around it. That is the rate of change of volume, total volume of oil. So I would need this, and I'm writing this right underneath here so we could see the problem. And I'm gonna show work on this. Some of you will just know what to write down, but we have to remember, what does that mean, right? And what that means is the volume at 25 minutes minus the volume at the start. And so this should tell us that we have to add that initial. And this is this, writing the wrong thing down, sorry about that. This is the equation that will give us, the volume of oil at 25 minutes. And how do we get our 2 points? The limits and the initial condition. So what that means is you must have that 60,000 and your bounds from 0 to 25. And then the integrand, this right here. And that gives us another 2 points. All right, everyone, I hope you're having a good day. Take care, and I will talk to you soon.